Melissa Lee, come all the way from Melbourne, Monash University, and she'll be telling us about elusive groups and bases.
Thanks, Alistair. And I want to open by thanking the organisers for organising this meeting. I can see that it's been a huge monumental effort to get all of this organised, even without the unexpected challenges. So thank you very much. And thank you for having me. Yes, so today I'll be talking about two different research projects I've been involved in recently that kind of have very different collaboration styles. So I kind of appreciated your talk yesterday, Cheryl. So I'm going to first talk about elusive groups and then talk about bases. So let's jump straight in. Okay, so section 1, elusive groups. So this was kind of a funny collaboration. Last year I had a PhD student called George Mitrovic visit me from the University of Auckland. And we looked at a paper based on elusive groups. I'll tell you a bit about that later on, with the view of extending it. And it turns out we were able to extend it, but instead of writing our own paper, we contacted the original authors and wrote a joint paper, which was really nice. So this is joint work with me and George, Jiong Chen, Bindo Xia, and David O'Brien. Okay, so where do we start? We're starting with derangements. So a derangement is a permutation that has no fixed place, okay? And there's a very old theorem by Jordan from 1872 that says that every finite transitive permutation group on at least 2 points has a derangement, okay? So recall from Cheryl's talk yesterday that a transitive group is a permutation group in which if you choose any 2 points, say A and B, you can always find a permutation that maps you from A to B, okay? Now I believe I've got some examples here to as a little warm up. Okay, so suppose you take Sn, that's obviously transitive because it's all of the permutations on 1 up to n. You can take probably the first permutation that you think of that might be a derangement, which is just the n cycle. So 1 goes to 2, 2 goes to 3, and so on up to n, and that maps back to 1. And this is obviously moving all of the points in a single orbit. But you don't even have to be that fancy. You can also specify that you have orbits of smaller sizes. So as long as you're not fixing any points, that's still a derangement. So here you can see I've got a bunch of transpositions, 2 cycles that I'm just swapping pairs in plots 1 and 2, 3 and 4, and so on up to 2k minus 1 and 2k. But you don't even have to have the length of your cycles all being the same length. So you could also take something like this, where I've got transposition and then a 4 cycle as a member of the alternating group A6, okay? And so here, this is a derangement of order n, this has order 2, and this has order 4. Now, in 1981, Fine, Cantor, and Shaker used the classification of finite simple groups to show that actually you can strengthen Jordan's theorem to show that every finite transitive permutation group, on at least 2 points again, has a derangement of prime power order. Okay, so not just any old derangement, specifically one of prime power order. Now, I don't know about you, but reading this, my natural next question that I'm thinking to myself is, can you actually extend this to say that we can always find a derangement of prime order? And the answer is no. Okay, so an elusive group then is a transitive group that has no derangements of prime order. Okay, here's the first example here. So M11, the Mathieu group M11 on 12 points, this action is 3 transitive. So M11 is part of a series of groups, the Mathieu groups, discovered in the late 1800s. And Mathieu was interested in finding out things about groups where instead of being able to map any 1 point to any other 1 point, you say, okay, can I map any 3 points to any other 3 points and so on. So this is multiply transitive. So this 3 transitive here means that you can take any 3 points and map them to any other 3 points, provided those points are distinct. So this group, it turns out in this action, is 3 transitive. There's a lot of transitivity going on, but it only has derangements of order 4 or 8. Okay, so in particular, that means that if you take one of these derangements and power it up to an element of order 2, it's going to fix some points. Okay, another example, which is maybe a little bit more involved, is that you take P to be a Mersenne prime. Okay, and now I'm going to take the affine general linear group, AGL1P squared, and that's just going to be all of my affine transformations. So I send x to ax plus b, and I take a and b to be in this finite field fp squared with the specification that a is not 0. Okay. Now, this group has a transitive action on p times p plus 1 points. And so if you observe that I've got p being inverse n prime here, this is just the only prime factors of this thing are 2 and p. Okay. And so what we have to do to check if there's a derangement is of prime order specifically, is check whether there's a derangement of order 2 or p, right? Because you'll need a bunch of cycles of order 2 or a bunch of cycles of order p and no fixed points if you're going to have a derangement. So if you sit down and work this out, you can see that there are no derangements of either of these orders, and so this is an elusive group in this action. Okay. So elusive groups actually have received a lot of attention, in part due to a conjecture which comes from combinatorics called the polycircular conjecture. So what's that? So the statement, it comes in a few forms, but the form I'm going to quote here is due to Klin in 1997, who conjectured that every vertex transitive graph has a semi-regular automorphism of prime order. Okay. Now, rather than explaining specifically what that means, I'm going to show you an equivalent formulation, which is more group theoretical. Okay. So the polycircular conjecture can be restated as the following. If you've got an elusive group, okay, say it's acting on a set omega, then you can always find a larger group J that contains that elusive group, such that you've got the same orbits on this direct product, omega cross omega, as your original elusive group G, but J has derangements. Okay, so somehow if you've got an elusive group on n points, then you can always go up a bit and find a bigger group that has derangements with the same orbits on this direct product here. Okay. Now, a lot of work's been done on this conjecture, and I'm not going to review the literature there, but maybe I'll state one of the most striking results, which is due to Giudice in 2003. So Michael Giudice showed that all quasi-primitive elusive groups are known, so he classified these groups. Recall yesterday from Cheryl's talk that a quasi-primitive group is one in which all the normal subgroups are transitive. So he classified all of the quasi-primitive elusive groups, and he showed that, unfortunately, none of them are counterexamples to the polycircular conjecture. So that means that in each case, you can always find one of these larger groups that has the same orbits on this direct product and has derangements. Okay. So if you're going to find a counterexample to the polycircular conjecture, then you need to look outside quasi-primitive groups. So what does that mean? You must be taking a group that has an intransitive minimal normal subgroup. Okay. Now, some such examples are known, okay, but many of them follow the same sort of recipe. What's that recipe? So most of them are split extensions of some group, which turns out to be an intransitive minimal normal subgroup by an elusive group. Okay, so kind of there's already an elusive group sitting underneath there. So you're kind of maybe taking an elusive group you already know and then forming an extension and making it. Okay. All right. Unfortunately, all of the known examples that are not quasi-primitive are also not counterexamples to the polycircular conjecture. So the polycircular conjecture is still wide open. Okay, so that's one motivation, is polycircular conjecture. Something that people have also been interested in is the set of degrees of elusive groups. Okay, so your elusive group is a permutation group. It's acting on some number of points, and so the number of points there is the degree. So what are actually the degrees for which you can find an elusive permutation group? Now, there are a few nice constructions, as you can see here, that given two elusive groups, or even just one, you can make a new elusive. So, for example, this first one here, if you have two elusive groups, G1 and G2, acting on omega 1 and omega 2, then the direct product acting on the direct product of those sets is also elusive. So you can see that the set of elusive degrees is closed under multiplication in particular. Okay. So yes, you can see we've got some other constructions there, but we'd really like to know what this set of degrees of elusive groups are. Okay. So let me show you some of the infinite families that we do know, apart from those in these constructions. Okay, so in the paper in which Fine, Cantor, and Shaker proved that you can always find a derangement of prime power order, they also present this family, which I actually think is the family that I mentioned previously, this AGL1P squared family. So here they've shown that you get this family of degrees here. So we've got a power of 2 times a Mersenne prime. Yes, that's the example I had before. Cameron et al. Showed in 2002 that the set of degrees of elusive groups also contains, what's that, 12 times a power of 7. And Michael Giudice in 2007 showed another infinite family that's maybe a bit more involved. So you've got this power of 2 here, and you need the power to be greater than this L, which is the, it involves this Mersenne prime here, P. Yeah, so we've got this really nice family here, but there's quite a lot of restrictions on the degrees. But something that we notice is that every known degree of an elusive group is divisible by both 4 and a Mersenne prime. Okay, and these constructions that I showed you earlier, where you take the direct product or something like that. Obviously, if you're divisible by 4, and you have an elusive group, and you take the direct product with something, that degree is also going to be also divisible by 4 and also a Mersenne prime. Okay, so we'd like to know whether this is always true. Like, is it a requirement that the degree of an elusive group is always divisible by 4 and a Mersenne prime? Okay, and so we need to perhaps think of a novel way to construct elusive groups if we're wanting to find possibly new degrees that are not divisible by 4 and prime. And to do this, and to find this novel way of constructing elusive groups, we turn to non-split extensions. Okay, so just to make sure everyone's on the same page, I figured I'd just quickly put a slide in here reminding you of the properties of split and non-split extensions. So a split extension of H by N, okay, so you've got these 2 groups H and N, is a group such that N is normal in your split extension G. You can, because it's normal, you can take the quotient map, and that quotient G on N is isomorphic to H. And also, not only that, you can find a subgroup isomorphic to H inside G that intersects N trivially. Okay, so split extension is quite nice. Non-split extensions have a lot of the same properties. So in particular, you've still got these 2 ingredients, these groups. N has to be normal in G, and this quotient is isomorphic to H. But now you're not guaranteed, and in fact, you're not going to be able to find a subgroup isomorphic to H inside G that intersects N trivially. Okay, and this extra sort of complication is seems to be the thing that allows us to construct new examples of elusive groups in this way. And the reason for that is if you have a elusive split extension, say H extended by N here, then it follows that H must be elusive. So somehow, even if you come up with a novel construction, it's kind of like H must be elusive, so maybe it's one of the known examples already. However, the same is not true for non-split extensions. Okay, it's possible that you don't have to have an elusive group here. As a quick side note, I will always use a colon to denote a split extension, but I will use a dot, possibly, hopefully always a little bit raised to denote a non-split extension. Okay. Right. So in this paper, this paper I'll say more about in a moment, we talk about the notion of overcoming. Okay, so here's the idea. So you have your H and N, these are the ingredients of your non-split extension. And you want this non-split extension, N dot H, to be transitive. And also when you map to the quotient, you can transitive action as well. Okay. Now what you do is you take a prime dividing the order of this group H. Okay. And we say that this extension overcomes P for H if we have the following. So H has a derangement of order P, so that would be bad in the split extension case. Okay, but somehow when we take this non-split extension, we have no derangements of order P. So somehow we get rid of these bad orders where we find derangements. All right. So let me show you a construction now. So I'm going to take G to be the alternating group A5. So that's all even permutations on 1 up to 5. And this group has a subgroup C2 squared. So two copies, the direct product of two copies of the cyclic group of order 2. Now, if you think about G acting on the cosets of H, this action has degree 15. Okay, so there are 15 cosets that we're commuting around. And if you investigate this action, you'll see that G has derangements of order 3 and 5, which doesn't look so great in terms of trying to construct an elusive group, but it has no derangements of order 2. Okay, so if we're hoping to construct an elusive group from this coset action, we would need to overcome 3 and 5 for G. So somehow we're going to have to make this extension that gets rid of all the derangements of orders 3 and 5. Okay, so we think up a rather crafty construction, if I do say so myself, but it arises from some quite natural modules for A5. So what you do is you take the fully deleted permutation modules in characteristic 3 and 5 over F3 and F5. So, you know, A5 is acting on 5 points. You say, okay, I'm going to create a vector space where each of those 5 points is a basis vector. And so my A5, I'm going to make a matrix group, which is just commuting around the indices of the vectors inside that vector space. Now, this thing is not an irreducible module, but you know, if you sit down, write it out, you'll see you can find the relevant submodules, quotient them out, and you get in characteristic 3 and 5, you get a vector space in dimension 4 and a vector space in dimension 3 that are irreducible modules for G. Okay. Now, we didn't just pull these out of thin air. You have to be quite careful because, of course, we want to construct a non-split extension. Okay, so we have to check what the dimensions of the second cohomology groups are to confirm that we can make these non-split extensions. Okay, so we can make them, but even that's not enough. So you kind of have to, something I discovered in this work is being able to form non-split extensions is not enough. You kind of have to get lucky with the way that things pan out when you do construct these non-split extensions to overcome these primes. Okay. All right. So we're like, okay, fantastic. We can construct these non-split extensions. So what we're going to do is we're going to take the direct product of, I don't know why I've changed my notation, but anyway, the cyclic groups, the corresponding cyclic groups that will represent these fully deleted permutation modules. And then we're going to take the non-split extension of that via A5, taking one of the non-split extensions in each case, and we're going to investigate what happens there. Okay. Well, fortunately for us, if you actually look inside this group, there are no longer any elements of order 3 or 5 that are not contained in just this normal subgroup here. Okay, so that's looking good for us. Okay. So then what we have to do is we can't just say, okay, make this act on C2 squared again. Perhaps we need to do something a bit fancier. So what we do is we take this subgroup of X, which we're going to call Y, where I still have my C2 squared. That was the subgroup of A5 that I was talking to you about before. But now we also are going to take this subgroup of our U cross V as well. And how do we choose this subgroup? Well, we look at the action of C2 squared on these fully deleted permutation modules, and the C2 squared actually fixes some submodules, in particular one of dimension 3 in characteristic 3 and one of dimension 2 in characteristic 5. So those are the ones that we take to form our subgroup. Okay, all right. So now we're going to look at the action of X on the cosets of Y. Okay. So we have no derangements of order 2 in X, since there are none in G. So we don't get any further elements of order 2 in this extension, so we've just got 3s and 5s here. So we're like, okay, great. No derangements of order 2. Now, I told you that there are no elements of orders 3 or 5 in anything except this normal subgroup here, this U cross V, so it suffices to check those. And we do computationally check that none of the elements of order 3 or 5 in this normal subgroup here act as derangements. Okay, so that's perfect. If you look at this group X, the input prime divides the 2, 3, and 5. We verified that there's no derangements of any of those orders. So we have managed to overcome 3 and 5 for G, and hence we've constructed an elusive group of degree 3 squared times 5 squared. Now, if you're paying attention earlier, you'll remember that I told you that every known elusive group has 4 and a Mersenne prime dividing the order. So we're quite pleased here because we, for the first time, to our knowledge, have an elusive group that's of degree an odd number. Okay. All right. So that's the construction of one group. But George and my contribution is that we showed that you're able to actually extend this to an infinite family. So here's our main theorem. So for every integer k at least 1, you can find an elusive group of degree 3 to the k plus 1 times 5 squared. So this is essentially just extending this construction to arbitrary powers of 3. And by tinkering with the construction just a little bit, you can actually also find an elusive group of degree 2 times 3 to the k plus 1 times 5 squared. And to our knowledge, this is actually, I think that might be the next thing actually. To our knowledge, these are the first examples of elusive groups with not only odd degree, but twice odd degree. Okay, so remember all those constructions where you like, take your known elusive groups and make new elusive degrees, you'll always get a multiple for them. So I'm quite happy with that. Just for the sake of being explicit, I've put the groups here. So you can see that we've got roughly the same group here for this explicit action. So our x is basically the same as the construction I showed you, except now we're taking 3 to the k there. And here, in order to get the twice odd prime one, we just swap from c2 squared down to c2, and that gives us the extra 2 that we. Okay. So we were very excited by this, Georgia and I especially being able to extend this to an infinite family. However, we quickly went to check whether the counterexamples of the polysaccharide conjecture and found, unfortunately, they are not. So the polysaccharide conjecture is still open. Okay. Oh, what have I done? Okay. Right. So this was a really fun project to be involved in, but there are obviously still many open questions in this line of research. So the paper that the 5 of us ended up publishing was sort of like a demonstration that you could use non-split extensions to construct elusive groups. And it was by no means intended to be an exhaustive search for elusive groups you can construct in this way. And so one of the open questions that I think is even listed in our paper is, can you construct lots of elusive groups using this method? We've shown one infinite family, can you make more? And in particular, can you find a counterexample to the polycircular conjecture using this construction? Now, I told you that, we've resolved this question of whether must always divide the degree of an elusive group, and the answer is no. But actually, if you remember from the previous slide, I had both 3 and 5 as divisors of those degrees. And so the question of whether every elusive degree is divisible by a Mersenne prime is still open. It would be really interesting to know the answer there. And finally, I would like to know whether 225 is the smallest odd degree in the set of elusive degrees. Now, our colleague Binjo, co-author on this paper, is adamant that this is the smallest odd degree of an elusive group. But I asked him for the proof, and he said, I just feel it. This is the smallest group. I just don't think you can do better. So I would really like to know. Yes, so this was a really interesting topic to work on. Okay, I believe that concludes our discussion. Yeah, go on, Adam.
So people feel why do people feel that polysaccharide conjecture should have a counterexample? Right? Or is it a nice reason to study elusive groups?
I think it's a nice reason to study elusive groups, and also maybe I'm not 100% sure of the all of the surrounding literature, but maybe there's also the sense that a proof seems hard, so maybe a counterexample would be easier to find or like require. I don't know, but that's my conjecture. All right. So I believe that's the end of my section on elusive groups. So now we're gonna talk about bases for permutation groups and their graphs.
Can I ask a question
Yes,
before section
go
2?
on.
So the obvious question, the example you gave us was a CLO2 subgroup of A5,
Yeah.
right? What happens if you try CLO2 subgroups of other things?
Yes, I have tried Silo 2 subgroups of other things. But the issue is somehow I've tried a lot of non-split extensions, but there seems to be something going on that you don't always get this nice construction where you are able to overcome the other primes. And it's still a bit mysterious to me as to what the actual requirements are to be able to make this work. Yeah.
Okay.
But yeah, I'm interested in exploring it further. Yep, go on.
So you extended the 3-5 example to 3 to the power of k,
Yeah.
5 example.
Yeah.
I assume it's not possible to do 3-5 to the power of k?
We did try very hard, but we were unable to get it to work. And so the kind of construction I've given you makes it sound like it was all done with matrix groups and so on. But actually, in our paper, the construction is given via group presentations. And so we were able to tinker with the presentation a bit to make it work for 3, but somehow when we tried the same tinkering for 5, it didn't actually increase the number of 5s there in the degree. So that was quite interesting, but we couldn't get it to work. Yeah. Any further questions on elusive groups? Okay, fab. Right, so now I'm going to talk about bases for permutation groups and their graphs. And this has been quite a rewarding project as well. So this was joint work with Saul, Camilla Rekveni, and Hongyi Huang. For one of these papers I'm going to talk about, and so we did a little bit of in-person collaboration, but by and large by email. And then the other paper I'll be talking about is joint work with my, at the time, research assistant, but now PhD student, Anthony Hassan. Okay. So I'm going to start off by telling you what a base is. So we're still in the land of permutation groups. Okay. So I'm going to take my permutation group to be G, acting on sim omega. Now, a base for G is a subset B of omega, whose pointwise stabilizer is trivial. Okay, so I take some subset of my omega and I say, what are the permutations fixing all of these points? And the only one I can find in my group G is the identity. Okay, let me show you some examples. So I've decided to go via graphs today. So let's look at this square here. What are the symmetries of our square? Well, we've got the dihedral group, so we've got 4 rotations, 4 reflections. Obviously, if I ask you what's the base of this, you could be cheeky and just say, well, just fix every point. And so you get the identity permutation by definition. But obviously, you can also find other bases. For example, if you take this point here, then you get rid of all the rotations because I'll always map this vertex here to somewhere else if I rotate, but I'll still have reflections. So I can take this point here and then I'll form my base. Okay. If I instead take this complete graph here, where I've got the symmetric group of degree 4 acting, then again, you could just be cheeky and say, take all of the vertices and that forms a base. But I can also take, say, 3 of these vertices here. And you can see that obviously if I fix 3 of these vertices, then this 4th one has nowhere to go. Yes, that also forms a base. Right, so for reasons I'll get to in a moment, we're usually interested in the size of the smallest base for a permutation group on its set omega, and we call this the base size of G, and denoted by this little b of G. Okay. So here are minimal bases in these 2 actions. So actually the ones I described are minimal. And as you can see, it can vary a bit from group to group, and indeed, depending on what your group is, you can have wildly different base sizes. Okay, so why do we care about bases? Well, they were introduced by Charles Sims in the early 1970s in the context of computational group theory. So they were introduced as a tool for algorithms for permutation groups, even though sort of informally the idea of bases had been studied for, I think, almost 100 years before that, but not officially defined as a concept. Okay. And one of the reasons why bases were introduced is because there was the question of how do you store a permutation group of large degree efficiently. So if I have a permutation group on 1,000,000 points, then obviously I don't want to do the naive thing of just telling you for each permutation where it sends those 1,000,000 points, because that would take a lot of storage in order to store each permutation. So bases afford us an efficient way of being able to store permutations of large degree, because it turns out that knowing a base for your permutation group allows you to easily determine whether two permutations are the same based on where they send a base. Okay, so you could store a permutation as a tuple that's the length of the size of a base, just saying where you send the base points, rather than this enormous tuples telling me where you send every point. Okay, so that's one of the reasons why we're interested in small bases. Okay, but bases are not always smooth sailing. So Peter showed in 1993 that there exists a universal constant C greater than 0, such that almost all subgroups of Sn, and here almost all means a proportion tending to 1 as n tends to infinity, have the base size greater than C times n. Okay, so somehow for most groups in a family, the base size increases with the degree. Okay, so that's not so fantastic if you're wanting to find really small bases for large degree permutation groups. However, fortunately for us, it turns out that lots of the permutation groups we care about do have small bases. Okay, for example, primitive groups. So Cheryl talked about primitive groups briefly yesterday. These are essentially, in some ways, the building blocks of arbitrary permutation groups. So Halassi, Liebeck, and Morotti in 2018, following up on work of Duyan, Halassi, and Morotti, showed that actually if you have a primitive group of degree n, then the base size can be bounded by this 2 times the ratio of these logs plus 24. Okay, so this is, this is much better than this lower bound, which is linear. Okay, that's pretty good. Quick detour into primitive groups, just in case we've forgotten. So a group is said to be primitive if it's transitive. So again, we're able to map from any point to any other point, and it preserves no non-trivial partitions of the set that we're acting. And the nice thing about primitive ones, as I said, every permutation group we can build up from primitive ones in some way. And primitive groups are also very nice because we have this Onan-Scott theorem that Cheryl also talked about yesterday, which classifies them into different actions for us. So we can kind of, if we're interested in exploring primitive groups, we can kind of look at them in each of these categories here. Okay, so we have this upper bound on base size due to Halassi, Liebeck, and Morotti. But it seems that apart from some kind of known examples of primitive groups that have large base size, it seems that many families of primitive groups actually have much smaller base size. And indeed, many primitive groups have a base of size just 2. So these could be enormous groups that are acting on millions upon millions of points, but you're always able to find 2 elements of the set that you're acting on, such that when you fix them, you get the identity. So Jan Saxel proposed, I think in the 1990s, that perhaps we should set about classifying the primitive groups with a base size 2. And this has been an area of a great deal of research. It was the topic of my PhD, and yeah, there's been an enormous amount of work on it. But this program of classifying primitive groups with base size 2 actually gave rise to a graph that was defined fairly recently, which is what I'm going to talk about now. So in 2020, Burness and Giudice defined the notion of a Saxel graph. So this was a tool to maybe study the abundance of bases rather than just existence. So what is this graph? So your vertices are going to be the elements of the set that you're acting on, omega. And I want my group to have base size 2, otherwise this graph is not very interesting. I'm going to put an edge between pairs of vertices that form a base for my group. Okay, so this will be non-empty, provided that the base size is 2, at most 2, I guess. If you had base size 1, this also would be very interesting. But anyway, so let's see an example. So here's our old friend, the square, with our dihedral group acting. So we've got rotations and reflections. Now, I showed you before when I was talking about bases to begin with, that 1 and 2 form a base for our group. Okay. So you have that these form a base. However, if you take diagonal points, say 1 and 3, that's not a base because if I fix those, I can still reflect along this line, okay? So I don't want to join those in the Saxel graph. So actually, if I take G to be this dihedral group acting on the square, then actually the corresponding Saxel graph is indeed the square, okay? Because adjacent vertices form a base, non-adjacent vertices do not. And a rather obvious observation, which will become apparent when I'm telling you this in just a moment, is that the diameter of this graph is 2. So if I take any 2 vertices, I can find a path of at most length 2 that gets me from one to the other. Okay, so Benes and Giudice defined this graph, and they showed that it has a lot of interesting properties. For instance, they showed that the graph is connected if the group is primitive. They showed that actually you've got a natural action of your group of base size 2 on the vertices, and indeed acts transitively. They also showed that this graph is regular, so every vertex is adjacent to the same number of neighbors as any other vertex. But perhaps most strikingly, they posed this conjecture, which I will call the common neighbor conjecture. So this is a conjecture for primitive groups of base size 2. Then they conjecture that every pair of vertices in the Saxel graph have a common neighbor. Okay? Now this is actually very strong because it's actually stronger than the graph having diameter 2. So if I have diameter 2, it means that for every pair of non-adjacent vertices, I can always find a common neighbor. But this conjecture says it also must hold for vertices that are adjacent. And it also seems very strong if you think about the base version as well. So anyway, this conjecture has been proved in a number of cases by various people. So in their original paper, Benes and Giudice proved this conjecture for primitive groups of degree less than 4096. So there's a database of these groups in GAP or Magma, and you can check them explicitly. They also show that the conjecture is true for sufficiently large groups of diagonal or twisted wreath type. So these are 2 of the types of primitive groups in the Onan-Scott theorem. Chen and Du also show that it holds in this case for almost simple groups with so-called PSL2Q, and in some other cases. And Benes and Huang show it holds for almost simple groups with soluble point stabilizer. And in joint work with Tomasz Kopiel, I also showed that it holds for certain types of affine type groups where the point stabilizers are sporadic. So we have a lot of evidence towards the common neighbor conjecture, but it's still open in general. Right. So the thing about the definition of Saxel graphs is they only really are interesting for groups with base size exactly 2. And as I said, we're very interested in primitive groups with a base size of 2, but of course there are all sorts of groups out there that don't have base size 2. So maybe we want to be able to generalize the notion of a Saxel graph that work for groups of any base size. So there's a couple of ways that you can do this. First of all, you could define a graph where adjacency is determined by containment in a minimal base. So suppose you have a group of base size 3, then you could still make a graph, but instead of saying that 2 vertices are adjacent, if they form a base for G, you could just say they're contained in a minimal base for G. We could also define a hypergraph. So we could have a vertex set being the same, and then we just say the edges are exactly the minimal bases. Okay, and I've been involved in projects that have made both of these generalizations. So let's start with the first one. So this is the joint work with Saul and Hongyi and Camilla. So the generalized Saxel graph of a group with base size at least 2 is exactly what I just said. You take your vertex set to be the set the points you're acting on, and you define adjacency to be containment in a minimal base. So here's our example. This is the same example as earlier. Now, I told you that any 3 points form a base because the 4th vertex has nowhere to go. But indeed, 3 is the base size for this action. Like you can't do better because if I fix, say, 1 and 2, I could just take the element of S4, which swaps 3 and 4, and that would be something non-trivial, which fixes these points. So this can't be a base. Okay. So what that tells us is that every 3 vertices are contained in a base for S4. in this action. So actually, the generalized Saxon graph is indeed just this graph. So that's quite nice that we're able to have this being the same. And again, let's look at the diameter. Well, every vertex is connected to every other vertex, so the diameter is actually 1. So you can always just go straight from whatever vertex you like to whatever vertex you like. Okay, so for this sort of generalization where now we're allowed to have groups of any base size, we were able to show that a lot of the properties that Monash and Giudice had still hold. So in particular, the graph is still connected if G is primitive. We still have this natural action of G on the vertices. It acts transitively, so the graph is regular, like every vertex has the same number of neighbors. We also showed that if G is too transitive, then the graph is complete. Okay, so that's fairly obvious. We also have some evidence for the common neighbor conjecture. So the common neighbor conjecture here is exactly the same as for the base size 2. So any pair of vertices have a common neighbor. So it turns out that when you increase your base size to groups of base size larger than 2, then all the calculations and techniques get significantly more complicated, but we were able to find some partial results. So we were able to show that if you have an almost simple primitive group, then the common neighbor conjecture holds for groups for base size at least 3, where you have sporadic socle, and also in cases where the point stabilizer is solid. Okay, so we're hopeful that in future we can prove this conjecture in more cases, but as I said, you increase the base size and everything becomes a bit more difficult. Okay, so we've got some evidence there. What about in the hypergraph version? So in the hypergraph version, again, this definition is exactly what I just said earlier. You still have the same vertex set, but now your edges are just the bases in size for your group. Okay. Right, let's see our example. I do apologize, my tick skills are not good enough to draw bubbles around things. So every 3 vertices, this is the same example from before, every 3 vertices is a base for S4. And so this hypergraph has edges just all the 3 subsets of 1 up to 4. Okay, so hopefully my tick skills will get better by the time my next speakers talk and I'll be able to have a more accurate diagram. But anyway, hopefully it's not too difficult to imagine. And here as well, we have the really nice property that, again, we have a lot of the properties of this original Saxon graph still holding in this context. So we have that the hypergraph is connected if the group is primitive, and we also have this transitive action of the group, and so we have regularity. But the completeness question becomes a bit more complicated now. So in the hypergraph, our definition of completeness is that suppose your base size is K, then every set of K vertices forms a base for your group. And because this is very strong, and in particular stronger than we had for the previous definitions, we're actually able to find a complete classification of cases where this Saxon hypergraph is complete. So I'm just going to flash up these cases. So we've got things like G being a Frobenius group. We've got other obvious things like alternating and symmetric groups and their natural action. So we're able to do a complete classification here, which was quite nice. Okay. Right. Now, in terms of the common neighbor conjecture, it turns out that if you just take the common neighbor conjecture as we had it in the previous 2 contexts and translate it over here, then actually you satisfy the common neighbor conjecture for the hypergraph if and only if you satisfy it for the generalized Saxon graph. Okay, so we figured that Saul and I and Hongi and Camilla had just finished work on the previous paper, and so I suggested to Anthony that maybe instead of trying to expand this, we could instead see okay, we're working with hypergraphs now, maybe we can have some slightly different notions that are analogous to the common neighbor conjecture and see what holds there. So we settled on 2 generalizations. So the first generalization is as follows. So you take your primitive group, it's got base size K. Now what you could say is that maybe what we'll do is we'll take edges inside our hypergraph and specify that they must intersect in exactly 1 point. Okay, so for graphs, this is not an issue because obviously the edges have size 2, and so you always have this if the common neighbor conjecture is true. Okay, now I had to exclude the alternating group and a symmetric group here, because this in their natural actions, because this would not hold for those, because the basis is so large. Well, and also because, you know, we have this completeness condition. Another generalization we thought of is that perhaps we could see if, you know, the common neighbor conjecture says that if you have a base size of 2, then every pair of vertices have a common neighbor. Well, we hoped that maybe in the Saxel hypergraph case, you could say that if your base size is k, then every k vertices have a common. Which sounded very strong to me, but I thought, oh, let's give it a go. So I'll just talk about each of these generalizations in turn. Okay, so here's the first generalization again. So with this assumption, we were able to show the following, that if you assume the common neighbor conjecture, then actually you also get this generalization. So even though this sounds stronger, this generalization, we get this implication here in the following cases. So base size row 7, which actually encompasses a lot of the primitive groups that we know of, where we know the base size. Groups of affine or almost simple type in a non-standard action. Okay, that's actually covered by the base size row 7 situation. Also groups of diagonal type with these conditions. Okay, so we're really hitting a lot of the Onan-Scott types here. Certain product type groups, so that's hitting yet another family. And we also were able to explicitly check this for sets of size of rows 128. Okay, so we have a lot of evidence that if you satisfy the common neighbor conjecture here, then you also satisfy this seemingly stronger generalization. Okay. Now I was really hopeful that the second generalization would be fruitful because it seems super strong, but it seemed like a very nice generalization. Now, unfortunately, it didn't quite work out, but that's okay. So for all k at least 3, we were able to show that you can find a primitive group of base size k, so I can find groups of all base sizes, where this generalization does not hold, and that's not fantastic. So we don't have the same common neighbor conjecture implies generalization that we had on the previous slide, but we did actually find something interesting, which is that if you have a primitive group of base size at least 3, and you do satisfy the common neighbor conjecture, then not only do you have that every pair of vertices have a common neighbor, you always are guaranteed at least 2 neighbors. Okay, so we kind of don't get the minimum possible connectivity. Okay, so these were some interesting generalizations of Saxel graphs that we decided to look at, but obviously there are still a lot of open questions. Okay, I'll stop there. Thank you.
Questions from Alyssa?
Can you bring back the last slide? Is there an obvious reason why that last bullet point shouldn't say base size k, then every 2 vertices have at least k minus 2 plus 1 common neighbors? I mean, like you've got the 2 that you're talking about making that graph, and then you should have the corresponding number of common neighbors available to you.
Making the corresponding graph.
So rather than when base size is 2, you have 1 common neighbor. When base size is more than 2, it grows from k.
Yeah, so I think it's the fact that we're working with hypergraphs, maybe our definition of connectivity is maybe slightly different in this case, right? So I would have to
Is there any obvious reason why that shouldn't be theoretic?
probably, but not off the top of my head.
More questions? None. So these are 2 sort of distinct talks, right? My question was kind of where like do they meet somewhere, these
They meet in interesting problems I've worked on recently. Yeah.
Okay. Then I'll finish with a comment that
Yes.
you missed an opportunity to mention that the polycircular conjecture remains elusive. You've missed that on at least 6 occasions.
It's fantastic feedback.
Yeah. You're very welcome.
Yeah.
Okay, if there are no further questions, let's thank Melissa again.